Okay, so welcome to the University of Adelaide's Electrical and Electronic Engineering 1A Module 2 in-practice tutorial Part 2. Today I really want to just go through some more advanced techniques for breadboarding as well as functionality of how a bridge rectifier works. Alright, so over here guys I've drawn already a mock-up of the breadboard. Here you notice I've also drawn on it some integrated circuits represented by the green rectangles. First thing I'd like you guys to notice is that in this bottom left hand corner of each IC, it's indicated by the dot on pin 1. So rather we always want to orientate each IC as we put it in the breadboard with pin 1 on the bottom left hand corner. Just by convention, so that as anyone walks up to an IC and yep, beautiful, pin 1 bottom left hand corner. Also happens so that the printing on the IC will also be able to be viewed correctly if that's the orientation. Next thing I want you guys to notice is that I also managed to include on this particular diagram here these black and red tracks. So yeah, black and red rows. This is meant to indicate the fact that eventually I'd like to run run ground and our supply voltage full length across the board. Not just as some of you might start doing, running 9 volts at the top and ground right at the bottom. This will start to make sense a little bit more as we go along, especially when you start building much more complicated modules. In particular, when you're starting to try and connect power to an IC. See, if I only had a supply rail at the top and a ground rail at the bottom, with this particular IC, if for example it needed to have a power connected to pin 4, as you can see here, then I'd have to run a wire over the IC, around the corner, into here. And likewise, if it needed ground on pin 10, I'd have to run a wire from the ground rod up and over and in. Generally, that's going to start looking quite messy, especially when you need multiple ground connections on the far side of an IC. You will be certainly doing that later in Module 4 and Module 5. Instead, if I run power and ground top and bottom, all I need to do is run a short line up to put a ground connection, and similarly for the VCC or 9 volts DC connection, as you see here. Same IC, same pin out, much easier to wire up, easy to see what's going on, less wires involved, and if the IC does happen to break and you need to pull it out, this IC is much easier to get out of the way with all these wires in the middle. So it's generally win-win, 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 win-win-win. Win for just more win for the win. Okay, so now we'll turn our attention to the behaviour of the bridge rectifier. Here over here, guys, we see a simple circuit that you will start building in early in Module 2. Just a simple power supply, so 9 volts AC coming in through a load resistor. Right, up here I've sketched a graph. I've labelled marked these. Got voltage in units of volts up here, time in units of milliseconds across the side. I've also done a scale on each axis. So here you find this black line underneath. It hasn't faded too much yet. That's the waveform I'm going to be seeing generated by this particular circuit. If we then introduce and try to plot over the same curve the next circuit we ask you guys to build, this is plotted in red. Now remember, this is a diode here, guys. A diode will only conduct in the forward direction, so current will pass through in this direction, won't go through the other way. So on the positive wave, the positive half cycle comes through here, passes through, no worries. Now on the negative half cycle, this side of the curve will be dropped. So negative half cycle, this will be the more positive edge, so the more positive voltage. Try to come through here, go through the resistor, hit this diode, no conduction. So as we see, flat line here. Again repeated. The more complicated circuit that we can look at, guys, is what we call a full wave bridge rectifier. This is called a half wave rectifier because we only see half a wave. This is a full wave. As can be expected, guys, I'll just quickly go through the waveform. We see this full green waveform here. This is because for this positive half of the waveform, comes through here, gets to this junction, can't go back through this diode. The diode will only conduct in the forward direction. Must come through this diode, through this load resistor in the same direction that we've seen before, and across here to this junction back here. and then because this junction, this point, this node over here is the more negative, comes down this path and through here, and out we go. Job done. So if we now also consider the second half of the waveform, this point here, that's when this half of the waveform, so for the lower half of the waveform, this side of the supply will have the high voltage, come down here, across, hit this junction, can't go back through this diode, forward conducts through this diode, down through the resistor in the same direction as we had before. Hence we can now plot this part of the waveform through here, up to here, has to go back out to the opposite side of the supply. Easy enough, hopefully everyone can follow that. So the capacitance, a capacitance is defined as basically the amount of charge that we can store on a device per unit voltage that we induce across it. So when we get to this point here, up on the wave cycle, the voltage that's across these plates, that's across this capacitor back here, is going to start to drop down. So therefore it's not going to be able to store as much charge. That charge has to go somewhere. It's not going to go back out to a supply line, it's going to have to go through this resistor. That's going to bleed, so this capacitor is going to say what we call, it's going to bleed current back into the circuit, and hence the voltage is going to drop down. It's going to charge back up, and once the capacitor is fully charged, it's then going to start to bleed more current back in the circuit. Because the voltage across that capacitor is smaller, therefore the amount of charge that's going to be able to store on those capacitor plates will be smaller. Therefore, and that excess, the charge that's not able to be stored on those plates has to go somewhere, so it goes through this resistor. Now remember, if this job of a resistor is to infringe current flow, to slow down current flow. If we didn't have this resistor here, and we just had a dead short, we'd see, bang, this curve just dropping straight back down. Okay. Likewise, if we had a much bigger capacitor, the amount of current that's going to flow through that resistor it will still be the same, but the comparative amount of charge that we're pulling off the plate with regards to how much was left behind on the rest of those plates, the capacitor, will be much smaller, and hence the voltage that's going to remain on those plates will be much higher. So for a larger capacitor, because the amount of charge it's still able to store, the voltage will be still much higher. Hence we see this dotted line here. And hence for a smaller capacitor, we're going to see this small dotted line coming down here. Because for the same amount of current that's going to be pulled off here, the voltage drop across those plates will have to be much smaller. It has to be much smaller because the amount of charge that's remaining on those plates is smaller again. Awesome. So hope that goes to your understanding and clears up a few issues.